All right, we're going to continue with our review for our final, starting with question 27.5. And I'm doing this on the iPad as opposed to what I traditionally use, so don't be too surprised if it's kind of weird. All right, 27 and a half. Sulfur dioxide is a gas that shows resonance. Resonance simply means that a double bond will shift from one part of the element to another. For instance, sulfur dioxide, sulfur is going to have 6 electrons. Each oxygen will have 6 electrons, so that's 18 total. 2, 4, 6, 8, 10, 12, 14, 16, 18. Our oxygen, you can see, has 8. This oxygen has 8, but sulfur only has 6. In order to make that work, we need to move 2 electrons
inside the infamous Viper Room in Los Angeles, California. We respond to a mysterious knocking
I didn't do that very well.
basement.
Okay, it's going to move, but it's not going to be... Come on, there we go. I can't get it to orient the right direction. But anyway, you can still see 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. What resonance means, because if I draw those 2 that I just moved as a double bond instead, that is one way that resonance could be. But double bond doesn't have to be on that side. It could be over here. And resonance simply means that it changes back and forth. We tend to put it inside square brackets. The point is that you need to be able to make sure that you count and see that everybody has 8 electrons. So the question is something like, which one of these is a correct drawing of resonance? As long as they all have 8 electrons, you're golden. All right, 29. Given the following molecules, tell what types of hybridization they have. So let's talk hybridization for a moment. We know s orbitals are circular, and then there are 3 p orbitals. The p orbitals are dumbbell shaped or peanut shaped, and each one of those orbitals orients on an x on the y-axis or on the z-axis, and then the s orbit will be in the middle. But that's for an atom. When an atom begins to bond, his electrons have to be equal. So they morph into that funky hybridization. And if you have an S and 3 Ps, you end up with the tetrahedral shape, where one... Oh, I wonder what my dog just did. Hang on. Teddy, what did you just do? What did you do, Teddy? Did you make a mess? I come out, and there are baskets on the floor. And I go up the stairs, and he's knocked over the basket stand. Probably looking for a tennis ball. Way to go, Ted. All right. Number 28, we're looking at hybridization now. Hybridization is just talking about what orbitals are involved. You'll remember that when we talked about electrons, we said that they could be in the s orbital. There were 3 p orbitals. There were 5 d orbitals. We discussed the fact that they feel analogous to a hotel, and that's when we use the hotel sheets. Well, when we draw compounds, we no longer talk about s orbitals and p orbitals by themselves. Instead, those orbitals begin to merge. If you have an orbital, or if you have an electron, or if you have a compound that wants to form bonds, it's going to form, the ultimate is to have 8 electrons in its outer shell. That is 4 orbitals, 2 electrons in each orbital. The standard, the s orbital and the 3p orbitals will form into that tetrahedral shape. This is what we would call sp3. So when you draw an electron or an atom, compound, Lewis structure, if you've got 4 bond areas, I don't mean a double bond counts as 1 area, but if you have 4 bond areas, 3 bond areas and a lone pair, 2 bonds, 2 lone pairs, those are all tetrahedral. If you have only 3 bond areas, usually you're going to have a lone pair in there, or 2 bond areas and a lone pair. This sulfur would be 2 bond areas and a lone pair. This is what we call sp2. If you have something linear, it's just sp. So if we look quickly here, beryllium chloride is going to have 2 bond areas. This guy is sp. Water, we've drawn before. Water, just trust me on the electrons, has 2 lone pairs, 2 bonds. He's sp3. If I draw IF3, we have a total of 28 electrons to put away. There's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So we have 3 bond areas, 2 lone pairs. You may remember that if we, sp3 adds up to 4 areas, but those elements that are in the 3rd period and beyond can have expanded valences, so this guy would be sp3d. SF4, same story. He's going to be bonded to 4 fluorines, and he's going to have 1 extra lone pair, so he's also sp3d. SCl6 is going to have 6 bonded chlorines, so he is sp3d2. Now let's put that to practical use. Question 28.5, identify the geometry. For our first carbon, he's got 3 bond areas. He's sp2. Our second carbon, 3 bond areas, 1, 2, 3, sp2. Our third carbon, 3 bond areas, sp2. Our oxygen has 4 bond areas, 2 bonds, 2 lone pairs, so he's sp3. And our nitrogen, 3 bonds, 1 lone pair, he's sp3. Now, 29 asks about pi bonding. I don't know if I can, let me just move him up. Can he move? No. I'm just going to have to look at him right here. This is an example of pi bonding. Remember we talked about sp3 and then sp2. sp2, we have sp2, 1, 2, there's 3 bond areas. But that third pi is not used. This is an S, a P, and a P. The third pi area comes up out of the plane, and the electrons basically go around like this. They can go back and forth here, they can go back and forth here. So you have, let me try this again with a different color. So here is our sp3 bond, sp2 bond, and here is the other P. And that electron is going to go back and forth on either side. Back here would be sp2. These two overlap here. Okay? Those two overlap. And that is what a P bond is. It makes a double bond. All right, we'll stop here for now. Thank you very much.